It's not.
Yeah. Okay, everyone. Good afternoon once again. So. Okay then. Afternoon. So. When I saw you yesterday, it's still buzzing. So when we met yesterday, we were discussing the definition of the derivative of a function. Okay, and the definition was this one here, definition 4.3, that a real valued function, a function defined on the real numbers or some subset of the real numbers, and taking real values is differentiable at a point A if this limit here, definition 4.3, if this limit exists. And we explained it in two main ways. As it appears there, it's examining the change in value that the function takes on between the base point A that you're interested in compared to the value it takes at another point X. And we explained how rather than simply looking at the difference f of x minus f of a, that really doesn't tell you anything about how the function is essentially, well, it doesn't give you a good picture of how the function is essentially changing because you don't know by how much you've moved away from A to this other point X. So you need to rather consider the relative change in value of the function. How the change in value f of x minus f of a, how that compares to as a proportion, say, of the change in value that you made to the argument of the function. So that's why it's f of x minus f of a over x minus a divided by x of x. We're looking for relative change in the value of the function between this base point A and another nearby point x. But to zero in on the essential behavior of the function at that point x, we take the limit of that relative change and see how it's behaving in the limiting sense as that other point x gets closer and closer to A. So that we constructed that kind of motivation or explanation for why the definition is as it is. We also gave a strong geometric argument for it, summarized in these two pictures here. Actually, that ratio of changes f of x minus f of a over x minus a, it's got a very clear geometrical meaning. It's what we call the gradient of the line. Or in other words, the tangent of the angle theta that the line, that green chord line makes with the positive direction of the x-axis. Okay. So that green line there summarizes the behavior of the function at the point A compared to at the point x. Okay, it's a line through those 2 points on the graph of that, the points at A and the point at x. And then the definition of the derivative then will be the gradient of the limiting line. Which line is the limit of those top green chords as the second point x gets closer and closer to the point A. Okay. And for nice enough functions, there is a single limiting line, which we refer to as the tangent line to the function at x. Okay, so those were things we discussed last time. And we spent a lot of time patiently explaining them to give them motivation. We also looked at the first couple of examples where we took some relatively straightforward functions, and then we could function f of x equals x, and f of x equals x squared, and we observed that we were able to derive their limits fairly easily directly from the to obtain their derivatives fairly easily directly from the definition. Okay. So we'll continue the discussion now. We also note that this process of differentiation can be applied again and again. And this gives you the so-called higher order derivatives. So you can speak of d2f dx squared, kind of how you read it in English, or d3f dx cubed. The second and third derivatives of f. These are, well, the second derivative is the derivative of the first derivative. The third derivative is the derivative of the second derivative. Okay, so you can form higher order derivatives by kind of repeatedly applying the operation of differentiation to a previous derivative. And some of these have very clear meanings when the value of the function is interpreted in a way that it often is. When the value of the function is giving you the position of something, the one-dimensional location of a particle or some part of the body, then the first derivative corresponds to the velocity of the object, and the second derivative being the rate of change of the first derivative, that corresponds to the acceleration. So the early derivatives have clear kind of meaning in engineering and physics sense. Now, the two examples we saw last time, we could continue to investigate lots of different standard functions and find the derivatives from the original definition. We're not quite going to do that yet, but we will make a lot of use of kind of the derivatives of standard functions. And the next two pages in the notes, these are pages 43 and 44, although they've got 8 and 9 at the bottom of them because they're extracts. They're the extracted pages from the standard formula booklet that we'll have in the summer exams. So you've got a lot of standard functions down the middle column there. Powers of x, logarithm, exponential, trigonometric functions, and so on. And on either side, well, on the left-hand side, you've got their integrals when they exist in a nice way. And on the right-hand side, you've got their derivatives. Okay, and there are various parameters in some of these questions. And the trigonometric ones is a kind of frequency-like parameter a there multiplying the x. So we'll often make use of this table of standard derivatives. And you've probably been making use of similar things up to now. Okay. Some of these particular functions we may come back and examine the arguments or examine the derivation of those derivatives, but maybe slightly later on after we've built up some of the theory. So as well as knowing the kind of derivatives of standard functions, we also need to know standard properties that the process of differentiation has. Okay? And these are summarized in a number of theorems here in section 4.6. And you'll recognize some of the concepts from earlier considerations where we're looking at properties of convergence of sequences, convergence of series, or limiting values of functions, continuity, and so on. Same themes come up again and again. See, what we've got here is an operation differentiation that we can apply to functions, real value functions. But we already know about a whole suite of standard operations that we can perform on functions. I'm thinking here of adding functions together, multiplying functions together, forming quotients of functions, and very major importance at composing functions. Putting functions in sequence in the sense of applying one function to the output of another function, constructing a composite function. And this is a way, using these operations in various ways, we can build complex, compound functions out of simpler ones. But now we have this new concept of the derivative of a function. It's an automatic kind of mathematical question to ask, well, how does this new concept of the derivative, how does it interact with those operations that you have in the functions? Can you say anything reasonable about what the derivative of the product of two functions will be? And we would hope and expect to be able to relate the derivative of the product of two functions in a nice way to the individual derivatives of, say, the two functions in the product. And also when you compose two functions together, when you run one function on the output of another one, that gives you a definition of a compound function, a complex function built out of the other two functions. Can you say anything reasonable about what the derivative of the compound function is in terms of the derivatives of the simple? Or is it completely unrelated? Well, thankfully, there is nice, strong, systematic relations between these things, between the derivatives of complex functions and and how those derivatives depend on the individual derivatives of the functions used to build the complex function. So the very simplest one of these is the linearity principle. So this deals with defining a new function. In the statement here, it's defined as a new function f is a linear combination of two functions g and h. So alpha and beta, we take as two fixed real numbers, fixed coefficients. We build a new function f as this linear combination alpha g plus beta times h. The question is, what's the derivative of f? So it works out very nicely that the derivative of the new function f is simply the same linear combination using coefficients alpha and beta of the individual derivatives of g and h. It's extremely nice behavior. Okay? You apply the operation to the linear combination f by applying it individually to g and h, and then forming the linear combination of those two. Nice property, which is true. We would like to convince ourselves that that's true by providing proof of it based on the definition of the derivative that we have and what we know already about limiting values of functions. Before we get into doing the proofs, we'll take a quick trip through some of the basic properties before we come back to start to prove them. The second one here, okay, a natural next question to ask after you've dealt with linear combinations is how to deal with products. Okay? So if we form a new function f as the product of two functions g times h, we have what's called a product. Okay? How to relate the derivative of the product to the individual derivatives of the factors. Okay? And you may well recognize this from previous studies. The product rule says that the derivative of the product f, so if f is g times h, the derivative of f is g times the derivative of h plus h times the derivative of g. Okay. We can see some examples of the application of these here. For instance, if we take the two basic functions sine x and x squared minus 1, well, strictly speaking, x squared minus 1 is like a linear combination of two more simpler functions, the square function, x squared itself, and the constant function 1. So you can see that expression y, which is a function of x, you can see it builds up out of simpler functions. The sine function, the square function, and the constant function 1. So if we need to obtain the derivative of y, we can obtain that from the known derivatives of the two component functions. So if we call those u and v, u is x squared minus 1, v is sine of x. Okay, using results we've already looked at, the derivative of u will be the linear combination of these two derivatives. Now the constant term, the graph of the constant function is just a horizontal line at whatever that constant value is. That would be the height on the vertical axis. And so all the tangent lines are horizontal, so they all have gradient 0. So the derivative of a constant is 0. And the derivative of the x squared function is 2x. So the derivative of u is just the linear combination 2x plus 0. 2x. And the derivative of v, well, that's one of our standard functions. We can go back to the table. The derivative of a sine function, sine of x, is cosine of x, where you've got a equals 1. So that's cosine of x. So therefore, we can obtain the derivative of the function y by inputting those two results into the product rule. Okay. So you have the derivative of y is x squared minus 1. That's the original function u, times the v dx, which is cosine of x, and plus the original function v, which is sine of x, multiplied by the derivative of u, which is 2x. Okay. Okay, so maybe at this stage, before going on to some of the other properties, we could go ahead and prove these. So we want to be able to prove these two properties of the linearity and the chain. Sorry, and the product. So for the first case, for the linearity, we have a function f defined as alpha g plus beta h. And we're just going to base this argument on manipulating the definition of the derivative using the principle of limiting values of functions that we already have. Okay? So we will, the definition of the derivative of f is the limiting value as x goes to a of f of x minus f of a over x minus a. Okay, that's the original definition which we introduced and discussed yesterday. But we now know what the function f is. The function f is defined in terms of g and h, like this. So we can put in the definition of f. So f is alpha g plus beta h plus x, and f of a is alpha g plus beta h plus a, and that's still all over x minus a. Okay, so we're taking the limit of that large expression there. Now we're aiming to show how this thing depends on the derivatives of g and the derivatives of h. At the moment, you've got g and h kind of bound up or mixed up together. So we would want to begin to separate them out. We can begin to separate out g and h away from each other by applying the definition of what a linear combination of functions is. The definition of a linear combination of functions applied to an argument x, so alpha g plus beta h applied to x, that is exactly alpha times the value g of x plus beta times the value h of x, minus, and then similarly down here, alpha g plus beta h applied to a, you've got alpha times g of a plus beta times h of a. That is all still divided by x minus a. Okay, so the justification for that step is simply the definition of addition and scalar multiplication for real value functions. Now, in the numerator, we just have 4 terms added together. Alpha gx, beta hx, minus alpha ga, minus beta hx. We just separate out the g and the h, bring all the g's together, bring all the h's together. So it's all over x minus a still. That's going to be alpha times g of x minus alpha times g of a. But while I'm at it, I may as well factor out the alpha. And it's beta times h of x minus beta times h of a. But while I'm at it, I may as well factor out the coefficient beta. That's good now. Now I have all the g's on their own and all the h's on their own. And that, what looks like a single fraction here, well, that single fraction, because the numerator is the sum of these two things, I can actually split the fraction up just into the sum of the two fractions. We've got the limit a of alpha times this fraction, g of x minus g of a over x minus a, plus beta times this fraction, h of x minus h of a over x minus a. That's just how you add fractions together, and how you multiply fractions by. So if the numerator is multiplied by a number, you can separate out that number in the alpha, and it multiplies the whole fraction. Similarly with beta. Okay, well now what we're looking at is a limit of a linear combination of these two quantities. Okay, these can be regarded as functions of x. So we can make use of what we've already built up, our knowledge of limiting values of functions. And limiting values of functions obey a linearity rule as well. Okay. And provided the limits of these things exist, I can split up this large limit as alpha times the limit of the first quantity, g of x minus g of a over x minus a, plus beta times the limit of the second quantity, h of x minus h of a over x minus a. Okay, the justification for that is the linearity of limits of functions, okay, which we've already discussed in beginning of this chapter when we're looking at limiting values of functions and continuity. Now, what I also need to be able to do that is to be sure that these individual limits exist. But of course, they do exist, because if you haven't already, we should now recognize that definition there is exactly the definition of the derivative of g of a. The limit of g of x minus g of a over x minus a. And similarly, this quantity here is exactly the definition of the derivative of h of a. So I know they exist because the theorem says, in the preamble to the theorem, it says, assuming that g and h are differentiable. So assuming g and h are differentiable, these limits exist and they are the derivatives. So what we have here is exactly alpha times the derivative of g plus beta times the derivative of h at x. So from the beginning to the end there, I've got exactly the linearity result. On the left-hand side of there, the derivative of f is equal to alpha times the derivative of g plus beta times the derivative of h. And that is true at every point A in the domain. Okay? There's no restriction, there's no special properties being used here at point A. This argument works whatever the value of A is. Okay? So this is true for all A. For all A in the domains of f and g and h. So therefore, it says that the derivative of f as a function x is alpha times the derivative of g of x plus h times the derivative of plus beta times the derivative of h. Okay. So that's the proof of linearity. See, it goes through quite nicely that the linearity of differentiation comes more or less immediately from the linearity of the limiting process, the limits of limiting values of functions. Okay? So it's really just the same property of the linearity of limiting values of functions. Any queries about it? Any questions you'd like to ask about that? About any of the steps in the argument? So we're confident now in that process, that principle of the linearity of the derivative. So our attention will go to the next one, which is the product rule. Theorem 4.6. And giving up. Okay, theorem 4.6. Now, I'll just preamble, or just before we go into this, we'll do a warning. We'll do it in red. What is the derivative not equal to? What is it important to say that the derivative of g times h is not equal to? Yeah, the derivative of g times the derivative of h. If that was true, it would be, you would call that property multiplicative. You would say that the derivative operator is a multiplicative operator, where you apply some operation to a product by applying the operation to the individual factors and taking the product of those. Okay? That is not true. But it is a mistake that people sometimes fall into when they're operating on autopilot a bit and they're differentiating large expressions. They sometimes fall into the trap of doing that. It's not a completely unreasonable mistake to make, because some operations are multiplicative. One particular one you'll have met recently is the determinant. The determinant of matrices. How do I take a determinant of a product of two matrices? Have you done the determinant? Function F, yeah. So what's the determinant of a product of two matrices, A times B? Well, the determinant is multiplicative. So the determinant of A times B is, in fact, the determinant of A multiplied by the determinant of B. So certain things are multiplicative. The operation of squaring, if you take a product of two numbers, so if these are just numbers, how do you square a product? Well, if you want to, if it's useful to you, you can express the square of a product as the product of the squares. Yeah. There's nothing special about squaring there. In fact, it works. It's a property of exponentiation, like raising things to any power. A product raised to the power n is in fact the product of the individual things raised to the power n. So in mathematics, lots of things are multiplicative. It's certainly useful when things are multiplicative. It makes it very easy to analyze certain situations. Okay? But the warning, the differentiation is not multiplicative. But that's not to say that the derivative of a product is completely unrelated to the derivatives of the individual factors. There is a nice, clear relationship, but it's given by the product. So it's actually, how have we written it? G, we put that first. Yeah, so it's G, it's the function G times the derivative of H plus the function H times the derivative of G. So it's if you like, a kind of a complicated type of multiplication. Although we don't say it's multiplicative. It's like multiplicative but with a twist, mixed up with linearity and so. Now this can also be proved using a similar approach to how we did linearity. So it just takes a little bit of a twist. So if we let f be equal to g times h, then okay, the first step is always the same. We just repeat the definition of the derivative. So the derivative of f is the limit f of x minus f of a divided by x minus a. Then we put in the definition of what the function f is. Function f is just the product g times h. And we used the same approach as before. Before, at this stage, we had the linear combination of g and h on the left and the linear combination of g and h on the right. And our principle was to separate out g's and h's away from each other. But that can't quite be done so simply here, because we're dealing with products, we're dealing with a different thing. But we're kind of half an eye on the result we're going to. We can kind of separate out the g's and separate out the h's in a way. And we did it like this, so it's still a big fraction over x minus a, and we find a convenient way to rewrite this product. And the way we're going to rewrite it is, yeah, well, so first of all, sorry, I just want to put in an intermediate step. First of all, the definition of g times h evaluated at x is indeed g of x, h of x. And the definition of g times h evaluated at a is, of course, g of a, h of a. Sorry, I just put that in as an intermediate step. That's just definition of the product of two functions. Okay, and then we rewrite it as follows. We take the quantity h of a, we multiply that by g of x minus g of a, and then we take the quantity g of x and multiply that by h of x minus h of a. So we're going from this expression here on the right to this one here. I'll put that on both screens. Now, why have we done this? Well, first of all, you just recognize that it's true. I mean, we did do similar moves when we were proving this kind of property for continuity, I believe. When you multiply this out, you do indeed get back to this expression here. You have g of x, h of x here, and you got minus g of a, h of a here. The other terms that are here cancel out. You got minus g of x, h of a, and you got plus g of x, h of a. So those cancel out. So this does indeed get you back to that. And of course, you can see the reason why we've done that is because in the difference g of x minus g of a, we have really, this is going to turn into the derivative of g, and in the difference h of x minus h of a, that's going to turn into the derivative of h. Okay? So we again split the fraction apart like this, and we're looking to use properties of the limiting value of the functions. So this becomes h of a times the fraction g of x minus g of a over x minus a, and it's the quantity g of x times the fraction h of x minus h of a over x minus a. Okay, that's just simply splitting apart the fraction as the sum of the two subfractions, if you like, and explicitly factoring off the g of x and the h of a. And so now it's not only the linearity of the limiting process of functions, we also, well, we need to use linearity to break up this plus here and say the limit of the sum of those two is the sum of the individual limits. But then the limit of this second one here, this is actually a product of two different functions of x, g of x on the one hand, and then this fraction which depends on x. And we have to use the property, the multiplicative property of the limiting values of functions. That the limit of this product here on the right is the product of the individual limits. Okay. So for all of this, using the limiting value of functions, I can split this apart. So the h of a is a constant as far as x is concerned. So I use linearity to split apart this plus here and to take that factor h of a outside of the limiting process. And then I need to use the multiplicative property of limiting values to split the limit of this thing into the product of the individual limits. H of x minus h of a over x minus a. Just about fit my bracket in there. So the justification is that for that is the linearity and product and multiplicative property of the limiting value of functions. Okay. The limiting process is linear, the limiting process is multiplicative. Then you look at the various parts you've got, and you see that they turn into the required result in the product. So you've got h of a there, multiplied by, now this limit is the derivative of g at a. As x approaches a of g of x, well, g is a differential function, so it is continuous. So the limit as x approaches a of g of x is g of a. And that final bracket there is exactly the definition of the derivative of h. Okay. So this is h of a times the derivative of g at a plus g of a times the derivative of h at a. Okay? So that just follows from the definition of the derivative and the fact that g is continuous. Okay? So that's the definition of derivative and the fact that g is continuous. G and h are continuous. But in particular, we're referencing it here, the fact that g is continuous. So you see we get exactly the expected expression from the statement of the product. That the derivative of f, here it is, f is g times h, so the derivative of that is h times the derivative of g plus g times the derivative of this was as required. Okay, so that's a proof of the product rule. Okay, so we are now forever secure and safe in our use of the product rule. It's seen the justification. Okay. Any questions about that? There's a little bit of a semi-magic step here, going from this expression to this. Why do you go to this? Well, you go to this because it works. But the motivation behind it is because you're beginning to form the expressions, these differences, g of x minus g of a and h of x minus h of a. You're beginning to form those, which will turn into the derivatives of g and h. Okay, so that's why it is we pass to an expression like this. So if you want to turn this expression into something involving the derivatives of g and h, you have to kind of draw those out. Okay? So this single difference of quantities here can be rewritten as this combination of the difference of g's and the difference of the h's. So as you look at it and you look at the result you're trying to get to, you see it's kind of less and less mysterious, more and more recent. Any comments on that? Okay, so the last 10 minutes or so, we'll be able to look at another couple of properties. Screen back up and try screen as well. Chain rule and the quotient rule. Let's look at the quotient rule first. So the quotient rule, jumping around a bit. So the quotient rule is kind of like the product rule in that it applies to functions where instead of multiplying them together, you divide them. So here we formed a new function y, which is the quotient of functions u and v. I'm sure you're mostly familiar with this. You've used this in your studies up to now. So there's okay, just a warning. So a similar warning with the product rule. The definition, the derivative of a quotient is certainly not the quotient of the derivatives. Okay? It may kind of work out like that by fluke for some very special cases, but in general it's not. Okay? The derivative does not behave like that. Again, it's kind of, you see something reminiscent of the product rule. You see a mixture of the individual derivatives of u and v, and they're both multiplied by the opposite undifferentiated function. But then it's complicated by there's a minus sign in there, and there's a v squared in the denominator of the whole. Okay. So this property is by no means obvious. I don't think it's that intuitive really when you first encounter it and start to think about what the derivative of a quotient might be. And to prove this, it relies on having a good understanding of what the derivative of 1 over v function would be, what the derivative of a reciprocal function would be. So when we come to, there's some examples of it being used there, but when we come to prove this quotient rule, we'll actually make use of the chain rule. So actually, I mean, you could go and prove the chain rule first and then the quotient rule. Well, we'll actually do it a bit back to front. We'll actually temporarily assume the chain rule is true, and prove the quotient rule, and afterwards we'll prove the chain rule. So the chain rule, finally, relates to, in some ways, the most, well, not the most fun, but equally as important, if not more so, than the operations of addition and multiplication for functions, is this operation of composition. The reason I say it's maybe might be more important is composition is a much more general operation you can do with functions. You can only add and multiply functions where you've already got operations of addition and multiplication available to perform on their values, on the values of the functions. Whereas composition of functions is something much more general and universal, because any kind of operation or happening, you can do them in combination with other ones. Do one happening first and then the other one after. So It doesn't rely on the notions of number or having arithmetic operations already existing. We talk about composing functions, even if the functions are just functions between arbitrary sets which don't have any algebraic structure or arithmetic structure on them. It's still possible and interesting to talk about the operation of composition. It's a much more fundamental, in some ways, mathematical operation. So we're very interested indeed, and it's very important all over the place, how the derivative of a composition of two functions, how that relates to the individual derivatives of the functions involved in the composition. So to spell it out here, is the statement of the chain rule. If we have a new function y, which is constructed as the composition of f and g, remember the meaning of this symbol, f circle g, you read that as f after g. So g is applied first to the argument, and then f is applied to the result. Composition of f and g. Then, when you have individual, if we call u the value of g of x and y then is f of u, the chain rule can be written as the derivative of y is, with respect to x, is the derivative of y with respect to u. So that's essentially the derivative of the function f. And then that's multiplied by the derivative of u dx, which is essentially the function g. Or, I normally prefer it in the other kind of notation. So this is the chain rule in the other notation. If y is equal to f after g. Yeah, y is equal to f after g, so y of x is f of g of x. Then the derivative of y evaluated at a point A is going to be the derivative of f evaluated at a point g of A multiplied by the derivative of the inner function g evaluated at a point A. Okay, that's the chain rule. The same rule is printed in the notes, but it's just written out in the alternative notation. Okay? So there's some examples of its application there underneath the statement of the chain rule. And for this week's tutorials, you look to the end of chapter exercises. I'm suggesting that you start to work through examples of the application of this. So this is all in part 4. It's a number of applications of linearity, product rule, chain rule, and so on. So you should start to work on those. There's also 1 or 2, slightly later, you see where you have got this x in the exponent position. Some of those later on questions, you might have to read ahead a little bit if you get to those to read about logarithmic differentiation in the notes. So we will discuss those. But we can see what's next on our plate. What's next on our plate is to deal with these, and I'll say more about them when we meet next week, but to deal with these properties of the chain rule and the quotient rule. And to see what the interaction between those two is in the proof of them. We're going to assume the chain rule, prove the quotient rule using that, and then come back and explore the chain rule. Okay, so thanks for your attention, and I shall see you next week.